Okay, here's the third in a series of videos on switching. And in this video, what I'd like to do is show you an example of a blocking configuration. What does that mean? What it means is that we've got this 6x6 switch. Here, we'll say the N is 6, so I've got 6 inputs and 6 outputs. And each of the switches in stage 1 is a 3x4 switch. Therefore, little n is 3 and little k is 4. And if I hook this thing up, I'm going to hook top to top. The top switch goes to all of the top input ports. The bottom switch goes to all of the bottom input ports. Top goes to all the tops again. And bottom goes to all the bottom output ports. Okay, so this is a 6x6 design, and suppose that I already have input number 1 mapped to, let's put all of our center stage switches in the cross configuration. And let's map input number 1 to output number 4. And let's map input number 2 to output number 5. Like this. And so by drawing these blue lines within the switching elements, I'm actually making circuits. So I have input 1 mapped crossing over to output number 4, input 2 mapped to second switch of stage 2 crossed over, mapped to output 4. Suppose also that I take input 5 and I map it to output 2, and input 6 is mapped to output 3. And so I've got 4 out of the 6 paths established, and so I can write 1 is mapped to 4, 2 is mapped to 5, 5 is mapped, the input 5 goes to output 2, and input 6 goes to output 3. And suppose now I want to add port 3 connecting to port 1. The question is, can I do it? Well, it turns out that when I'm coming in on port 3 here, I'm forced to go down to one of these bottom 2 switches because the paths to the top 2 switches coming from this upper stage are already used. These 2 paths are already used here. Okay, so I'm forced to go to these bottom switches. But on each of these bottom switches, I've already got a setup where I'm forced to go to the bottom output switch. Okay, and this is an example of a blocking configuration where we can't do it. We cannot add input 3 to output 1. Okay, and the reason is that all of the outputs from the input switch are taken up, and all of the outputs of the bottom 2 are also taken up. Okay, and as I showed in the lecture, this is a very simple case, but if you make some switching examples, it's very easy to come up with a wiring diagram where you've used some paths and you can't add another path that gets you your new hookup. Okay, so for instance, we can't add from 3 to 1 here. And in general, what we're going to find is that the switch configuration will be strictly non-blocking, strict sense non-blocking, if k is greater than 2n minus 1. So if 2n minus 1 is less than or equal to k, then we have what's called strict sense. There's no k in strict. sense non-blocking. Okay, or SSNB. And what this means is that you can always add your new path without rearranging things. Okay, it turns out that if k is greater than n and strictly less than 2n minus 1, then we have what's called rearrangeably non-blocking. And this is abbreviated RNB. Okay, so you can imagine in this situation that we could probably figure out a way of wiring up this 6x6 three-stage switch so that we had all 5 of these connections. We just have to rearrange things a little bit. Okay, we can get these 4 to exist by some rearrangement and then add this one finally. And so all we have to have is k being strictly greater than n, or greater than or equal to, I'm sorry, than n for rearrangeably non-blocking situation to occur. The problem with a rearrangeably non-blocking switch is it can be very difficult to write the algorithm that figures out how to rearrange the connections so that you can create your new voice circuit. Okay, and it turns out that if k is strictly less than n, then we are in a blocking. Then our switch is of the blocking variety. Okay, and so these are the 3 classes of three-stage Clauss switches, and it depends on the number of outputs of the first stage relative to the number of inputs to the first stage. So it depends on little k and little n. And by the way, if k is less than n, then we have what are called space compression, space compressing switches at the first stage. And if we have k greater than or equal to n, if k is strictly greater than n, then we have what are called space expanding switches. Okay, and so k strictly greater than n is called a space expanding switch design. Okay. Okay, so I'll leave it at that on this video. That's an example of a blocked configuration.